Hello, my name is Michael Cardei, and this summer I worked on context-driven roadwork detection and localization for autonomous vehicles. Autonomous vehicles perform well in routine standard settings, but have been shown to struggle in more complex environments. Specifically in roadwork zones, which can sporadically emerge, there's been shown to be a lot of difficulties navigating these areas. Furthermore, the sporadic nature means that GPS systems don't accurately identify these areas. Therefore, a robust detection and localization of these areas is critical for effective navigation. Previous works use either object detection or transfer learning for this purpose. The methods that use object detection lack context and inter-object relationship and just general scene comprehension. Furthermore, because they only look at one object or a few objects, they bypass crucial elements and objects that could signify the presence of roadworks. Those methods that use transfer learning make no efforts towards localization and fail to show generalization capabilities in unseen cities. The dataset used is Robotics with 5,322 front view road images. These images are manually annotated with roadwork-related classes. We use an additional 4,759 images without any roadwork for detection purposes. These images are from 19 cities across the US and have varying conditions. Shown here are two example images with the annotations demonstrated. For this method, we use two main models for two main tasks of detection and localization. For detection, we utilize transfer learning by fine-tuning the EfficientNet model on our dataset, with images split between the presence of roadwork and the absence of roadwork. We then train it for classification purposes, so it can discern typical aspects of roadwork and a variety of different elements that might be involved in roadwork. For the localization, we fine-tune the MaskR CNN model for instant segmentation purposes. As demonstrated here, we take the original image. We then use the fine-tuned EfficientNet to determine whether or not there is roadwork present. We also take that image and run it through the instant segmentation model to generate the mask. We then apply the Convex Hull algorithm to form more blob-like structures of these objects and to get a more work zone mask rather than specific objects. If there has been determined to be roadwork present, we overlay the image onto the original. If not, we just maintain the original image. These are the evaluation results for detection on both same distribution and out of distribution. So what that means is that the diagrams on the left show the results for the model trained and tested on all cities, whereas on the right, we train the model on specific cities and test on unseen cities. This is to make sure there's no unintentional memorization or any spurious correlations. We notice a decrease of 0.01% in the ROC score. However, this result is rather insignificant and shows strong overall capabilities. For instant segmentation, we have a variety of work zone semantic classes to capture a more holistic view and various representations of what road work can look like, including cones and drums, area boards, signs, and workers and work vehicles. These images demonstrate the original images on the left and the mask from the instant segmentation model on the right. These are some of the instant segmentation results. I'd like to point your attention to the main results are the overall AP of 0.363 and the mean average precision for various classes, which vary in terms of how well it works per class. This also illustrates the different classes we take into consideration when determining if there's a work zone present or not. We have two different evaluation methods for localization. The first one I just previously showed you is for the specific instant segmentation objects, whereas this one is more for the work zone evaluation. So for this, what we do is we create another class, another annotated class, that's the work zone class, and we annotate specific areas, more general zones where work zones are present. We then have the predicted mask with the Convex Hull algorithm applied to it, and we have 5 metrics to evaluate how well this performs. Overall, we notice an intersection over union score of 0.4 with the Convex Hull is applied. I have now 2 demos to show. These demos are videos from within vehicles, similar to the training data set or from the data set we used. And they begin where work zone is present and then drive out of work zones to show how well it performs, just general example. The numbers on the top left is the detection output for how likely there is a work zone present. So I'm gonna play the demo. I have another example to share. It has a different work zone environment and setting, so I'll share this one as well. Lastly, we also created a classical natural language processing method for added context and understanding. So we took these images and we used scene text recognition and detection to pull out any keywords that might be relevant to our task. Um, we also then do some filtering to make sure that we only incorporate the important words. Um, we then do phrase formation with dbScan clustering to form sentences based on the different grouping of the words pulled. We then extract the TF-IDF features and train a multinomial naive Bayes model. Some example results and outputs can be seen in the image at the bottom left. So we developed and validated a deep learning method for precise detection and localization of roadwork zones and front-facing road images. We also tested the model's generalization capabilities on unseen road settings. Overall, we achieved an AUC score of 0.99 for detection, IOU of 0.4 for localization, and for specifically object detection, we achieved a MAP of 0.363. Future work involves integrating the NLP pipeline in the previous slide with the localization results shown throughout this video. I would like to thank the Robotics Institute Summer Scholar Program. I'd also like to thank Dr. Nada Seaman, Dr. Tambiro, Rachel Gerson, and the Illumination Imaging Lab for their mentorship and guidance. Thank you.